Okay, so if you see to a great extent, that analysis is the one of the most important parameter which engineers should focus. So as a civil engineer, what is the importance of it and why we say the word structural analysis, so that will focus. So as we all know that for an engineer, it is important ultimately to see how the basic requirements are going to be there for any analysis and which are the parameters which are going to be focused for a design. So if you see in a glimpse that the analysis part is not only significant because it is going to establish a foundation for the design as well as the structural parameters which are there, considering the internal as well as the external loads as well as forces which are going to act on a particular building. Here on the screen, you can see a simple figure which is of a building showing the twisting due to the unbalanced forces and how it is going to behave. Just a schematic diagram is being shown. So ultimately, if you ask that what analysis is or what do we mean by analysis, so here we'll see the thing for it that, sorry, the behavior of a structure is going to function according to the design period for its intended use. So it is not only that we want to think upon any specific building for a specific period. Each building has a specific design period, each has a different purpose, each has different materials also that we are going to see later on. But we have to analyze that particular building for that particular behavior. So all the structures are ultimately going to be linearly elastic, and based on that we are going to calculate whether the internal forces are there which are produced due to the design loads. We can also say that the material strength is always assumed. So we have predicted the strength of any material, say for example steel or we say concrete. Those strengths are being predicted and the characteristics are determined based on that, and then we are proceeding on to the design part. So if we mainly see, we have up till now we have heard of the words bending moment, shear force, deformation, torsions, deflection. All these are ultimately computed so as we can analyze the particular building, and based on these values, so these values are ultimately our analysis values, and based on them we are going to design according to the loads and the governing forces. So here a very brief example is being given, which almost I guess everybody might be knowing, but just to brush up other things, simply supported beam is being shown, having both the supports as hinge over here. A 5 meter span is being taken and a UDL of 10 kilonewton per meter is being taken. So the first beam which is shown over here, if you focus, this is for a hinge beam, and here this is a fixed beam. So for the same span and same loading, what changes can we see, that we are going to see. So this obviously can be calculated manually, but just I've taken a screenshot from stat itself. And if you see the maximum deformation which I get in case of a hinge beam which is having a simply supported condition is 2.133, while in case of a fixed beam of a same span same loading it reduces drastically to 0.417, means almost 5 times. We have heard this thing that when the support is changed from simply supported to fixed, what happens? So we can reduce the deformation up to 5 times of it. If I focus on the bending moment parameters, here I can see the maximum bending moment which is being produced due to simply supported beam. We all know the equation W square by 8. So by that we can get a value of 31.25. And the same thing if I highlight in a fixed beam, that value is distributed to a fixed moment as well as the simply supported moment at center. So that value again is coming to be 10 and 20 respectively, which ultimately again is reducing to one third of the extent of the reinforcement which is ultimately going to be provided at the center. So now these all is analysis. So what is design ultimately? We are going to talk obviously about analysis. Then why should we focus on the parameter of design? But as design is ultimately a parallel thing which is going to be known or should be known while analyzing the structure, we should be knowing both of the parameters. Only one is not going to help out either of. Okay. So when we want to fix a section size, Okay, say for example, I'm talking of a concrete section, whether it is 250 by 400 mm a beam, whether it is 200 by 400 or 500 mm. So what section size I should take, that is again going to be determined by the characteristics strength of the material, whether I'm going for M25 grade of concrete or M20 grade. Again the whole beam size is going to be changed. Okay, and so we want ultimately the beam or our column or any structural element to sustain the bending moment, shear force, torsion, as well as deflection, which is ultimately analyzed due to the design loads, which we are going to ultimately assume and design the whole building accordingly. And as code has given the permissible limits, we have to check them within the permissible limits. So if you see over here that the design period of any particular structure is to be done till a certain point, and it has to sustain all the loads and the deformation under a normal conditions. Normal conditions means whatever we have assumed while design, and that same thing should be done parallelly, and it should focus throughout the lifespan of that thing. Say if I'm designing a beam for 10 uh, years, so that same thing, sorry, so same thing should be done parallelly. So the basic requirements for structure analysis, if I focus, here we have, it should be designed according to the type of the structure, the type of the purpose of the use, and according to the design we have to analyze the particular structure. So whether the building is a residential one, a commercial one, whether it is an road, excuse me, sorry, whether it is a road of a flexible or rigid pavement, whether it is a bridge of a minor or a major category, whether it is a residential one, commercial, educational one, the industrial building or tall buildings. Now you might be thinking that what is the purpose, how it is going to influence, so that the purpose or use of the structure is also important in analysis, because we have to take a parameter based on use of the building also. So that also we are going to discuss further on. If you see over here, the materials to be used for the structure are steel, wood, rubber, plastic. So any members or materials can be used, and it is to be accordingly modeled or analyzed for our particular structure. Then again an important parameter is the location of the structure, where it is there. So the seismic zone, as we all know, when we lie on a particular country where we are uh, regioning, the seismic zone is going to affect, and based on that we have to analyze the building. Not only seismic zone but coastal area, the wind parameter which is going to be there, the wind velocity which is going to be adjusting to the other building, where a building is there at a particular height, so that all parameters are to be considered. The soil explorations, which are also important, which is already being discussed. Yesterday also we had a very nice presentation consisting of soil importance and its uses, that how SBC is going to import of it, and whether it is lying on a low lying area, whether water table is impacting on it or not. So these all parameters also are to be uh, considered while analyzing any structures. Here I have a very short video to be shown. Uh, it is basically focusing on the structural uh, connections, and how connections are important and what it governs through it. Uh, Please excuse me for a minute. I'll just play the video. I guess it's not playing here. I hope the screen is visible.
Yes, yeah.
Yeah, I just play on the video. Just a bit. Probably Probably many might of you have seen this video, but still for a regular glimpse, how it impacts a very visual thing is being shown to us.
Nirav, yeah, actually screen is not visible now. It got disconnected somewhere. You're muted, muted. You're muted, Nirav.
That what an engineer must think about it. Is the screen visible?
Yes, sir. Yes, sir. It
Yes,
is.
sir.
Thank you, thank you. Okay, so for an engineer, what we have to analyze is, the first thing is we should think how it is going to be predictive. Means we should be knowing the circumstances which are going to come in future, so that circumstances we should be able to design our particular building, and for designing the particular building we have to analyze in that particular situation, considering those situations. Now, which are the situations which we usually feel? So normal, the dead load, live loads, and all we are knowing, but these are some of the situations which we cannot say that it is going to surely come, or it is surely not going to come throughout the lifespan of the whole building. We cannot say that a building will definitely strike an earthquake or not, whether it will strike a cyclone or not, whether it will be subjected to impact loading or not, whether a blast can occur in that particular building or no, whether a fire can be there. So these are some of the situations where we have to predict a thing, and we have to make our building which is capable of resisting all of these, or we can say majority of these. So we, as an uh, analyzer, we also know that either we consider the wind forces, or either we consider the seismic ones to be acting on a particular time. It is not that we consider both of them, but the one which is more vulnerable we are usually considering our buildings. So, pertaining to the wind loads, which is a very famous example from 1889, which is still standing, the Eiffel Tower, which we know is 300 meters tall, and which was designed and which was analyzed by Gustave Eiffel in that particular situation, that he has analyzed in such great manner that it is still withstanding all the forces, and there were no softwares also available through which we could analyze right now. So when we, as we know, it is not constant with height nor it is constant with time. Right now there may be very less wind, and after some time there may be high intensity of wind which is flowing at 40-50 meters per second, and so on. Okay, also it is possible that on one side, as it is windward, it will be creating high pressure, and on the second one it will be creating a low pressure. So that was also to be considered during these points. The second important parameter, which I usually feel is important, is the seismic load. Now, for the seismic load, if we see, and not going far away, just pertaining to our country, if you see, these are the zones where it is highlighted, and we can see that majority of the land. So here the percentage has been calculated, and it is almost a 60%, or about 60% of land is under moderate to severe seismic hazard. So if you just look out to the cities, the four major cities, Delhi, Mumbai, Kolkata, and Chennai, are lying either in zone 4 or zone 3. And the major cities are being listed over here. But to again say that Patna, Darjeeling, Amritsar, Ahmedabad, Surat, our own cities which we in Gujarat, we are mainly located. So Gandhinagar, whether it is Rajkot, whether it is Surat, whether it is Vadodara, all are in zone 3. So they are more critical. Bhuj, as everybody knows, that it is in zone 5. So that is one of the major segment where we are usually worried that due to Bhuj, what is going to happen to our nearby cities. Now, uh, we are going to directly focus on earthquake as an parameter, and why it is there, where we are going to talk on it, because uh, whether any structure of any height we consider, earthquake has to be considered for that particular building, whether it is a 4-story, 5-story building. Nowadays compulsory or mandatorily we have to consider that earthquake force and analyze a particular building. To be very precise, even if I design a single story building also, then also have to consider where it is located and how it is going to impact due to the natural hazards that I have to consider. So it has an potential which can cause a major consequences on not only infrastructure but lifelines also. We know that thousands of people are being uh, injured, and we can say even have lost their lives due to casualties during the earthquakes. Okay, so the conventional design code which we are usually referring, that is IS 1893, is a force-based design code. Now, force-based design is suited to design the things which are permanently applied to a particular structure. If we say, there are two types of methods which we can deal with, if we see that also. Okay, so these are the two methods, force-based method as well as second is a performance-based method. The force-based method is the one which usually code is governing us, and we design our buildings according to that. So here a pictorial view is also being shown that how it is to be done. So when we go for an force-based, what do we do usually is we design the maximum demand which we expect, and the seismic performance how it is going to be there. While in the second case, when we go for a performance based design, we go in a reverse manner, that how we want our building to react during that particular performance. So when we go for a performance based, it will be in a non-linear case. When we go for a performance based, it will be in a non-linear case. So also if you see over here, then the different methods of seismic analysis are there. Uh, Starting with the linear static analysis, which is the equivalent static method, which we go using the codes. Second is the linear one, but the dynamic analysis, that is a response spectrum analysis. Then moving on to the non-linear cases is the first non-linear static analysis, that is the pushover analysis, and the non-linear dynamic analysis, which is the time history analysis. Now when we go for different types of analysis, how it is to be considered, we'll just see briefly, and then we'll move on to one particular method in a depth. So firstly, if you see for time history analysis, uh, how it is being governed, that we'll see that the name itself is says that time history analysis. We have to analyze any particular building, any particular model, any particular structure based on the historical data which we are having, which is based on time. Means we have to take a particular earthquake data which is already existing. Say for example, I want to analyze my particular building which I am designing right now to resist the earthquake which had come in Bhuj. So I will take a time history. If I want to analyze my particular building or my particular structure up to that extent that it can withstand the Kobe earthquake which had come of so and so intensity. So at that particular thing, we are going to take that data which is already available through the past. So that's why the name is time history analysis. The mathematical model is being created and it is subjected to accelegrams from the earthquake records which are available, and the building is going to be analyzed according to that. So just if you see in a glimpse, what is the basic procedure? We won't go in much depth, but yes, the basic procedure is we are going to take these records and we are going to input into our model, which we are going to analyze using software, whether it is a SAP, whether it is ETAP, whether it is StatPro, or any other program. We are going to input the time history as regular intervals, and then we are going to run the model and we are going to see how it is going to be based. So the mathematical model is going to be based, and each floor, which we consider here only a single story floor, is being shown to us, and it is being shown as a lump mass. So if we have 4 or 5 story building, or whether it is 50-story building, each floor will be considered as a lump mass, and then they are going to be analyzed. Now comes the equivalent static method, which is the very interesting case, I would rather say, because in majority of the cases we deal with this, whether we want to even go for an hand calculation, this is the method which is being used. Now the method is based on base shear according to the weight of the structure and the governing forces. Okay, now which are the important parameters? If you see, probably all might be knowing the equations which are displayed over here. That is, the time period is obviously depending on the height of the structure. Then we usually calculate AH and multiply it with W to calculate the design base shear. Now, the factors which are there for calculating AH, if you see over here, that is Z by 2, I by R, and SA by G. So Z is obviously the zone factor, which we have just now seen that according to the zone where the building is being located, we have to take the zone factor as that. Importance factor, where I said that whether our building is an residential building, commercial building, or whether it is a public building, whether it is the hospital building, importance should be given. So that role plays over here, that importance factor of that particular building should be 1 or 1.5. We all know that our building during an earthquake is going to be subjected to some or the other harm, but we do not want the public buildings, we do not want hospitals, we do not want our fire brigade stations to damage any point of time, because they are the sources where the casualties are going to be taken, or they are the buildings where from where we can save the other structures. So they are given an higher importance, which is almost 50 times more. That's why the importance factor is 1.5. Rest we all consider as 1. The response reduction factor, which for ductile listening we consider as 3, and we also consider 3 and 5 also. 5 is for ductile listening and 3 is for OMRF rate. The SA by G factor, which is based on the time period. So if you see all the parameters which are listed over here, we are going to focus on this one parameter, which is response reduction factor. Now the response reduction factor which is there, the code is saying that take this factor. Okay, now how it is evaluated, or from which parameters they are governing, that we don't know. Okay, now we don't know in the sense that it is being said and we blindly follow that we don't have the solution to use any other value. Should I take 5.1, should I go for 5.2, or should I go for 4.8? Will it be convenient? We don't have an option because we have to follow the Indian code over here, and we have to design according to. Now, how is that particular factor decided, or how code is giving that particular factor? That we are going to discuss today. So, firstly, before saying the breakout of the R value, we'll see that what other codal provisions are taking the value of R. What we have said over here, that Indian takes 3 or 5. What other countries takes? Let's have a glimpse of that. So if you compare with Europe, Japan, and Mexico, the R factor which is there is based on the time period. So when we have a time period of 0.1 seconds, it is taken as 2.3, 3.3, and 2.5 respectively for the respective countries. And when the time period increases, the R factor is also going to increase to 5, 4, and 4. So this is being governed by these countries. Looking on further, I don't know why that is not being displayed. Okay, just for a minute, we'll see from this slide itself that the ductility factor which other codes are governing, that is AACE, is also giving a variation of 3, 5, and 8 depending on the dissipation energy, how it is going to dissipate, whether it is a low dissipating one, whether it is a medium dissipating one, or whether it is a high dissipating one. So based on that, the code is being analyzing the structures. The Euro code is also governing according to that ductility class also. New Zealand code is again bifurcating into short period and long period based on the time period, that how much value is to be taken. And if we focus on the Indian code, right now it is being displayed on your screen. You can have a view for that. That for OMRF, what I said, that is ordinary resistance moment resisting frame. So that is 3. For SMRF, that is special RC moment resisting frame, it is 5. When we have in prohibited zone, that is 4 and 5. For shear walls, it is again values 5 and 4 respectively. Okay. Now, as we have seen that according to the Indian code, it is clearly visible that ZI SA by G is based on the seismic hazard estimation. When where your building is there, suppose it is in Vadodara city, we have to take the value as Z as the third zone. Whether your building is a importance normal residential building, you have to take 1 as 1.5. SA by G value we have to take according to the time period. So there is no other factor which is focusing on the structural aspect of the particular building. So the R value which is there, that is going to be included in our design, and that's why we do I upon R. We divide by the factor R and reduce to that extent because we want to dissipate the energy through inelastic behavior. Okay, so R factor ultimately acts as a linkage between the elastic level as well as the design level, and it also provides a link between the linear and non-linear behavior. So we all know the behavior of any particular building according to the material which we are selecting, whether it is a structural steel or whether it is an reinforced concrete structure, the R value works according to that. Okay, so it is also essential tool where inelastic plays a role and earthquake happens over there. So we are going to reduce our force to that extent so we can uh, allow our building to perform well during the cases. Now, if you see the R factor is also known as force reduction factor according to the FEMA code, modification factor according to ASE, and behavioral factor according to the European codes. So here we call it as response reduction factor. In various countries, it is being known by the different behavior which they observe, because they feel that it is reducing the force. That's why they call it as force reduction factor. Some say that we are going to modify the response of the structure, so they call it as response modification factor. And one analyzes the building and feels that it is focusing on the behavior of the whole building, how it is going to perform, so they call it behavioral factor. But here in, according to Indian Goal, we call it as response reduction factor, because we are dividing the whole terminology which is displayed over here by the value of R. We are calling it a response reduction factor. So what ultimately does it, it reduces the design forcing in an overstand factor. When we design it according to the seismic codes, it is going to reduce to that extent, and going to account for what? Damping, energy dissipation, and overstrength of the factor. Now these are the terminologies which are very important, and based on that it is giving the value. But the breakup is not given in the Indian code. They have directly given us the values. Okay, so here a pictorial view is being shown, in which we see the lateral forces over here and lateral displacement. So what happens due to earthquake? We know that a building is going to move on and it is going to laterally displace. So here we can see an elastic behavior of the structure, which ultimately now from a elastic one converges to non-elastic, or we can say this is the actual response of the structure which we get. So we have to design the force according to it, and we have to reduce it, that the building should not reach up to this level, but we have to reduce it to this level. That's why we are reducing that factor. Another view is there also, that also I'll show. So this is the terminologies which I was sharing with you. Okay, so the maximum force, if you see, overstrength factor, whether we call redundancy factor we call, or the ductility factor, these are the three major factors on based of what our R value is being divided. So R is the multiplication, or we can say the product of all these three factors, which is the ductility factor, redundancy factor, and the overstrength factor. We are going to see one by one all of them, and we are going to each of them simultaneously. Sorry, I forgot to say that if anybody is having any doubt, even in between, please feel free to interrupt and ask. Sorry, I forgot to say in the start of the lecture. Okay. So if you see over here, the overstrength factor is having the concept, and the components which we say we are going to be dividing into three major sections. The first is the overstrength factor. We are going to decide what is the strength of the factor, and we are going to reduce to that particular extent. So for this analysis, we convert from a linear stage to a non-linear stage. So for even deriving to this one factor, we need to go for non-linear analysis. So that's why this is one of the reason why code is for elastic static, it is simplify giving a value as 5 or 3. Okay, if that was not given to an, and if the factors are directly available to us, we have to mandatorily do a non-linear analysis, which is a pushover analysis. We probably are aware of pushover analysis. If not, we'll have a glimpse of that too. Okay, so the overstand factor is the ratio of the actual base shear to the design base shear which we intend to design the particular building, and the strength which we are going to estimate is according to the ATC 19 or ATC 40, we can say, because Indian code is not having that particular uh, codes available. We have to adopt the ATC code for our analysis part. Okay. The pushover analysis is also used to construct the graphs of the base shear as well as the roof displacement for any given frame, and based on that we can understand where our building is going to perform in that particular level. So the first factor we can calculate using this equation, that is RS, that is overstrength factor, Vmax and Vd, the ratio which is being displayed over here, that is corresponding to the actual yield of the structure. How much actually it can yield our particular structure, that we are going to denote by Vmax, and the code prescribed design base shear which we can find out using the given equation Z by 2 I by R and S by G. So that is the code prescribed design base shear. So we are going to use nonlinear analysis and we are going to find the maximum shear which is possible for any particular structure, and for this we are going to use the codal position, and then we can find out how much over strength we are analyzing in a particular model. Second factor is the ductility reduction factor, which is denoted by R mu, and it is the ratio of the maximum deformation to the yielding deformation. First, we have uh, first parameter was mainly focusing on the base shear. Now, the second parameter is focusing on the yielding of any building. So, based on that, the factor can be determined. Now, as there is no code prescribed, even there also they don't have any code which is prescribing this particular parameter. So, according to the research available, two major researchers have given the values or the equations to find out the ductility reduction factor. So how we can find out that is either by Newmark and Hall. Two authors are there which have combinedly worked extensively in this area and given the equations. And Miranda and Barreto, these are again two researchers who have worked for it and found out those equations. So we'll have a of that also. So ultimately, if you see from the pictorial view, what is a ductility in normal sense also we can say that the maximum ratio what we get upon the yielding ratio what we get, that is ductility of that particular member, structure, or any particular element, that how much maximum it can yield, how much maximum it can deform, and where the linear to non-linear stage starts. We all probably know the tensile steel bar which we used to do in our graduations level, and we even make our students perform the tensile test on MS bar. So here we are aware of this graph, but here we have a necking zone and then it goes to the cup and cone failure later on. Okay, but from where it changes from the linear to non-linear stages, this is being determined, and based on that we are going to find out the ductility. Now let's see the equations where the two authors have worked out. So first, Newmark and Hall, since 1982, just to again I would highlight it is 1982, which is before my birth, I would say precisely. So before that, they have found out these equations and yet they are not implemented in our codal provisions. So that is a lag where particularly a researchers finds. So here if you see, based on the time period of the building, they have converted the equations that how your R mu is going to deform. Okay, so if your time period is less than 2 seconds, 0.2 seconds, sorry, so then your R mu will directly be equal to 1. If your time period is between 0.2 to 0.5, which is an intermediate period, then we have to use an equation of under root 2 mu minus 1. And if your time period is greater than 0.5 seconds, directly it goes into the long period zone, and directly we can take R mu value as mu. So we have already seen how mu is calculated. So this ductility is ultimately your mu. So delta ultimate upon delta yielding. This we have already seen through the graph. So this equation, how we are getting this equation? This equation again is given in ATC 19. So based on that, the mu is being calculated, and based on mu, R mu is being computed. This equation is given by Newmark and Hall. Second parameter which is being focused is by Miranda and Bertiro. Now what they say is in after almost say a decade later on, say 10 to 12 years back, then they started more developing equations based on the soil values also they wanted to impact on that. So based on that they have found out these equations, that r mu will be based on mu minus 1 upon phi, where phi is a factor which is considering time period also, ductility factor also, and it also goes on to an extent that how much the logarithm value of your time period is based on that. Here if you see over here, only one factor is there which is clearly stating that when my time period is between, say for example, 0.2 to 0.5, I have to consider this particular equation. So whether it is 0.2 or whether it is 0.5, I have to take the same value. But if I want for an intermediate zone, whether it is 0.21 and whether it is 0.49, it would have a drastic change. So that lag was found out by these two researchers, and they have found out these equations. Ultimately, the purpose is the same, to find out the ductility reduction factor. The third factor which is there, which is a redundancy factor. The redundancy factor is purely based on the structural system, how we are making that particular system. For example, whether it is a 2 bay frame, 3 bay frame, 4 bay frame, how many number of columns you are having in one line, in one orientation. Based on that, directly this value can be computed. Okay, so for a non-redundant system, the failure of the equivalent of the failure of the whole entire system would be causing. Say for example, if I only take a normal 2 bay frame and an earthquake is going to happen, so the redundancy factor which is there, that is going to be a lesser value. When it is having more number of columns which is arranged to it, it is going to provide stability, and that's why the redundancy is going to increase. So here you can see, again this is provided in ATC 19, that when the number of vertical lines of the seismic framing, what I call it as bay, when they are 2 bays, you can take the value as 0.71. When it is 3 bay, you can take it as 0.86, and 4 and more than 4, directly we can take the value of 1. So when we have any frames, 4 or more than 4 bay lines which are supporting the seismic frames, we can go directly for one value. And when it is of lesser value, it is going to impact in the R factor, and it is going to again reduce that factor and ultimately going to increase the capacity of our particular building in that particular extent. So let's take an example to understand that how is it effective to consider this, or is the code giving us whatever it is giving, or whether whatever it is coding is perfectly correct or not. So here an example is being taken, a very brief or short example we can say, to understand what is the importance of R factor, whether we should take the value directly or whether we should incorporate it, and uh, on what other basis it should be decided. Here a very only one example I've shown over here, which is a G+4 building. So only one story is being considered. This analysis can be extended again to number of stories also. You can vary the number of stories. The soil type here is considered medium. We can again change the type of the soil and conduct the same study also. So even if fixing the parameters, is it really impacting? Let's check that. Then varying the parameter obviously is going to impact. So the importance factor which is being considered is one. The concrete grade, as we have considered in RCC structure, the concrete grade is M25, which is usually done nowadays. Fe415 is the grade of steel. Story height is 3.2, and the importance factor, as it is general commercial building, we have taken it as 1. The seismic zone, as it is 5. Let's focus for the worst case. So it is being considered 5 over here, and the zone factor is being considered accordingly, that is 0.36. So here this frame is being considered, for example, that we have taken 3 bay. The frame, the base size is taken as same, that is 5 meters, and the height as 3.2, which is explained to you. Okay, so this is being explained over here. Now the building model is being analyzed using SAP as a tool for better, faster analysis. And also, we have considered 5 cases. Now, only governing for one case is, I thought that would it help or not. So, here for that particular thing, more 4 cases are taken. Now, the parameter or with the video which was shared with you was having the connection as important parameter, plus bracing was an important parameter. Now, whenever we analyze any building, the main area where we should focus is analysis. Okay, now how we should analyze that building when we are considering all the loads, how we should analyze the building, that is very one important parameter, and based on that the significance is decided for it. So we are going to signify not only the importance of R factor but the importance of analyzing a building in that particular model. Now analyzing the building means what? We, any building which we usually analyze in any software, whether it is SAP, ETABS, StatPro, or any others, what we do is we uh, give the frame, we draw the frame, we analyze the thing, we give the dead load, live loads accordingly, and then we place the wall loads as a UDL, isn't it? We, what we usually do, we place the wall load as a UDL on the wall, give the load and analyze the building. Now, obviously, loading part is perfectly analyzed. There is no harm in giving that loading, because actually that wall is going to be there on the particular building. So you are giving that particular loading, but the wall is having a particular strength, that wall is having a compressive strength, that is a picture. But that wall which is there in the video, when we see that the bracing element, when it was added, the whole behavior of the structure which was directly falling down resisted on a particular path. Here the analyzer comes into picture, what we should analyze and in which manner, whether should I simply place the load, whether I should consider that as an strut. So that strut is going to work as in bracing. That bracing which is there, actually, uh, most of us have a concept that steel is only used as bracing, but that isn't true. Some of us have also worked on that parameter, that the wall which is there also act as an member, and we have seen uh, in past earthquakes, if I focus, that in past earthquake what happens, that which floor fails, usually which floor fails in earthquake. If I have G+5 building, and if I have parking at the ground floor, then first floor, second floor are normal floor, is what is going to happen? Usually what happens, which floor fails first? If anybody could draw out the attention.
Don't know, sir.
Which one? Sorry.
Don't know. Sorry.
Okay, you don't know. Okay. So, if you have, even if you see the photographs of any structure which has failed during earthquake, you will usually find the ground story, the parking story columns failing, and so the whole building collapses. Correct or not?
Yes, from the base. It will collapse from the base.
Yeah, from the base. Yeah, from the base. So that base is a weak story. We usually technically call it as weak story. Why it is a weak story? Because on the building frames which we are considering like this, okay, everywhere we have a wall, and this is not supporting any masonry wall which usually other floors are being supporting. So due to this
Okay.
behavior, this all floors are going to be having more strength, and this is going to be the weak one. That's why we technically call it as a weak story. And due to that, this fails, and if this fails, logically whole building collapses. So that parameter is whether very important, whether that particular parameter incorporate into our model or not. So when you are not incorporating and when you are providing, actually you are safer. As a designer, we need not to worry that we are not considering that wall as an element and we are not designing. अगर हम नहीं consider करते हम safer ही है. But why not to take the advantage during the analysis part? So that is also being focused in this particular example. 5 cases have been taken with infill walls. Now one is going to be a bare frame. Bare frame means I am not considering any wall element over here, and I'm going to run it normally without any masonry infill wall. Second is I'm going to take a building with all masonry infill wall. In one, I'm going to take only at the periphery. I'm going to take only at the periphery. Two more models I'm going to consider in that stage, that I'm going to make them as weak story. So ek, from the lower portion I'm going to remove it, and one I'm going to remove at the middle story. So let's understand that behavior, how it is acting according to the analysis part. See, the design part is obviously determining the dimensions of any particular element, whether it is beam, column, or slabs. But how to analyze it, whether we should consider this or not, and if you are considering, what are the pros, what are the cons, we are going to see in this particular example. Over and above, we are also going to compute the R value, the R factor, which directly is given as phi in our Indian codes. Okay, now as I've said that infill wall, which is a very important element, that has to be computed and that has to be assigned building. So to compute that, again, research has been done. It is not given, and in 2016 version, now it is being incorporated. Up till now it was not there. So the infill wall, now the equation is being given as same thing, but before that it was not there. So we place this whole wall as in strut. Now what should be the dimension of the strut, that we have to determine. So this width of the strut is being determined by these two parameters, that is alpha h plus alpha l, which is ultimately which is based on the masonry properties and how it is going to be determined. So when we have this wall, actually all the columns and the beams filled up with whole masonry, we can assign this in this particular manner as a diagonal strut in one particular direction, either this direction or this direction. So these are the components using which we can find out the width of the particular uh, masonry strut element. So here the specific weight usually is being considered as 18 kilonewton per meter cube. It may be considered 17 to 20. So I have taken as 18. The modulus of elasticity is given by this equation 240 Fj, where Fj is the mortar strength, which is the mortar is usually weaker than our masonry. So concrete element. So that is 15.1 megapascal. So the E value is being computed in that sense. Poisson ratio is 0.25. The coefficient of thermal expansion, we are considering that. The G value, we know this equation that G is equal to E upon 1 plus mu. So that also we have been computed. And the outer thickness of the wall and inner thickness of the wall, which we have considered throughout the analysis, is 230 mm and 115 mm, because that is used practically. So we usually, if we go on field, we see 9 inches wall. So 9 inch converting to mm, we have as 230 mm. The RC sections, if I precisely say, the reinforced concrete sections which are governing are being taken of columns are of 500 by 500 and the beams are of 300 by 500 mm size. The reinforcement of the column are 8 20 mm diameter and 6 16 mm and 4 16 mm accordingly. Now, how this size is governed, that also we can quickly see that The loading which we usually give on our structure, that is live load, can be considered as 3 or 4. The live load for the roofing is 1.5, floor finish we consider as 1, and the slab as 3.75 kN per meter square, considering 0.15 meter thickness. So considering these load, firstly a preliminary size is to be governed. Even for analysis, we have to give the size of that particular element. Then and then we can run the analysis. It is not that we this is a design part. This is a preliminary design parameter which is required for analysis, because even while running the analysis we require how much dead load is going to come on the structure. This all is fixed. I agree with you all that this all is fixed, that the live load is going to be there, but what is the size of the member? तो member का खुद का weight कितना होगा? So how can we determine that particular weight? So that for that determining that weight, we require size of the member, and for that size, this is the preliminary design calculation which we have done. So the dead load, as I said, 3.75, how it is there, that is just multiplying the density, which is 25 for RCC, getting the value. The total load is 8.75 kN per meter square. Factoring it, we get this value, and the total load is 196 kilonewton. Now, the total load which is going to be distributed on the 5 columns, multiplying with 5, and we get as 984 kilonewton. The topmost column is going to bear this much load. So considering self weight of the load of the column itself as 10% more, using the equation which we all know these things. Okay, so we can find out the area of the concrete and then decide the dimension of the column. That should I go for 400 by 400? Should I go for 500 by 500? That also we can go by trial and error, but this hardly requires any, it requires less time. So this method usually I adopt. I preliminarily decide the sizes based on the loading which is given to us. Same way for the columns, same way for the beams. Okay, the span is being there, the UDL is being there, converting using the equation 0.166 FCKBD square, which we all know, and assuming the beam size, and then governing the size accordingly. So this is the procedure how we can determine the preliminary size of the beams and columns, and how we can analyze a particular structure. Now for even finding out the base shear, we require the size of the member. So that's why everything is incorporated, and here the 5 cases which we have discussed is being listed over here. That a normal building is one which is not having any walls. Second case where infill wall is there, but only at the periphery. Inner walls again are not being given any strut element. Then the third model, every wall is given as a strut. The fourth, as we said, weak story, and the fifth as a soft story. Whenever the wall is not there or any intermediate story, that is considered as a soft story. Same way as we consider on ground floor, same thing is there, only the parameter is technically known as a soft story. So the design uh, is governing the particular elements, and based on that we are analyzing the weight of the structure, the time period, age, and finding out the base shear. So this is the design base shear which we are getting through the equivalent static method as per the given codal provisions, that is 1893. Okay, now, so the code part is over here. Now again we require the second base shear, which is the actual base shear. How we can get that? So for that we need to run the pushover analysis. So the static pushover analysis is partially and relatively simpler intermediate solution to a complex problem, which is going to incorporate all the imposed load on the structure, because in pushover analysis we are going to push a particular structure up to a desired level. Pushover analysis is a very basic method, a very useful tool we can say for a non-linear static analysis, which is ultimately going to evaluate the limits up to which we can finally get the desired drift or the desired force in a particular segment. Okay, so the analysis is going to be terminated or stopped at a target displacement. So that displacement is very well known to us at the starting only, and we are going to design the particular beam for, or the column, or the whole structure to be precise, for that particular target displacement. Okay. What we usually do is, the loads what is there, it is actually acting on the building, that is known as the gravity loads. So firstly the gravity loads are there, and then the monotic load is going to be acting on the building in case of horizontal loads for your pushover analysis. uh, SAP is being used as a tool over here to analyze the whole models. So a brief screenshots are also being shared over here. If you want to use SAP as an tool, how you can do that, just for a ready reference I can say. I'm not going to go into software part a lot, just a glimpse of that. Firstly we are going to give define the mass sources. The mass source is the whole, the building as an whole. Then we are going to define the different load cases, whether it is a dead load, live load, then response spectrum load, push over analysis. So we are going to determine the push, and then we are going to decide the acceleration, whether it is going to consider into which segment, whether we are going for a linear case, whether we can go for a non-linear case, whether we want to include the p delta effect, or we want to discard the p delta effect. That again is a very different topic where we can undergo research and understand a lot of parameters. Then we are going to from which code we want to adopt. So we have used FEMA, and we are going to define the hinges as per the given table. We can also define as per our choice, but they are predefined as per FEMA over here. So that is being displayed over here, that how it is being taken, whether it is for beams and whether it is for column. So the concrete beams are usually governed by M3 as the load case, and your uh, columns which are there are considered as M2 M3 as a load case. Now you might be thinking what this hinges is, the previous slide which I have shown to you. If you're not aware, I'll just explain in brief that hinges are the places when, in case of any earthquake, if earthquake hits to a structure, or if any horizontal load, not only earthquake, if a high horizontal force is struck to the building, what is going to happen? The building is going to fail. Now the failure is going to occur at particular junctions. So that junctions are very critical, which we define as hinges. So if you want to see this structure which is shown over here, this is the beam hinges which we define. This is the column hinges which we
Sorry for the interruption, guys. I guess there is some network issue with Nirav sir, and he possibly left the meeting. So kindly wait for a few minutes, and he'll be back again over here. Sorry for the interruption again, sir.
Extremely sorry, I had a power failure. Extremely sorry for the inconvenience.
No problem, sir.
I don't know. This is also harassing me today. The screen is not moving. Yeah, we were there into the point that the hinges which are there on actual structure, on the actual structure, if you see, these are the hinges which is formed due to the seismic force on actual structure. This is being seen to us that the column is going to fail like this, the beam is going to fail like this. These are the column failures. This is the places where usually the column fails. Here you can see. So these are the critical points where the hinge forms a pattern of a failure. So we are going to design the particular building in a particular manner that the point where it is critical, we are designing those elements more. Now for designing those elements more, we have to analyze in that particular manner, because design and analysis both are simultaneous parameters. So if I want to design that element, I want to provide more reinforcement or more concrete section on that particular area, I have to analyze in that particular segment. Now for analysis, I have to make that as a critical junction. So these junctions, here you can see the beams and here you can see the columns. So these are the critical junctions where failures are predicted. So there we are predefining them as your hinges. After defining the hinges, we are going to run the analysis as we do in normal static cases. Here we are going to run a pushover analysis and we are going to get the graphs, okay, for the base reaction as well as the displacement. So the base reaction versus displacement, if you see over here, for all the 5 buildings we have plotted the graphs over here. So we can see how the behavior is changing according to that. And after getting these pushover curves, we are going to get or focus on the performance point. Now performance point is a very important point where our building is going to perform. The technical name is given also considering a very important parameter, that performance point, the point where the performance, where we require as an analyzer, we are demanding that okay, this is the performance point of the particular building. The meaning of the word is usual meaning of, as we use in English, that what is the performance of this particular case, this particular student or so and so. So the structure which we are analyzing, uska performance kitna hai, how much is the performance of that particular building, that we are going to find out. Now how we can find out? So the performance of anything which we find out are based on two things. One is how much it can do and how much we expect from it. Okay, so if I'm expecting 10 out of 10, that is my demand. So that I'm going to expect, that is my demand. And how much is my capacity? I know that even I cannot score 6 marks and I'm expecting 10. So that is my capacity. So wherever my capacity and demand is going to meet out, that score I am going to get. So it may be possible I can stretch a bit capacity or I can reduce my bit demand and come to a point where my performance is going to meet out, and where my capacity as well as my demand meets. That score will be my performance score, whether it is 6, whether it is 7, whether it is 8, and so on. In the same manner, the structure is also having a particular capacity. That capacity is based on the seismic demand which we are going to give to it. So based on that demand and based on the capacity, we can find out the performance of the building. So this point where your building capacity curve, which we have seen over here, so this base shear and displacement graphs which we are getting, capacity, it is converted to capacity spectrum, and from that capacity spectrum we are going to plot the demand spectrum. This type of curve we have usually seen our codes, okay, from where we take the time period. So based on that, where your time period and your capacity meets at that junction where it cuts this capacity curve, or we can precisely say where your capacity curves cuts your demand curve, that particular point is your performance point. And from that particular performance point, the value of the base shear we are going to take as the actual base shear. Okay, and that point where we have to determine the RS, what we were focusing on, the overstrength factor. So the same models which we have analyzed. So here the hinge formations which were given to the structures. Here I guess it is more clear. And the first one, we don't have any uh, wall element which is placed. So we don't have any strut element which is assigned. Okay, so this is for the outer and inner face. Here in the ground story, we don't see any element over here, and we can see there is no strut element provided in the middle floor. So these are the arrangement where we want to see how it behaves during the analysis. Again, drawing your attention, all the span are same, all the loading is same, even the ground condition is same, nothing is being changed. Only the way of how we are going to analyze it is changing. Are we analyzing it as a strut on all the parameters, on only the center parameters, only some story, all the story, that we are focusing right now. So now, yeah. So we want to estimate the Overstand factor, which is RS, that is maximum base shear, which we have found out through the software, divided by the design base shear which we have found out through the code. Again, R mu we can find out, and then we can find out RR. So based on all these equations, let's find out one by one. So here a typical, only one for one building or one model it is being showed to you as an example. The rest will be directly tabulated as an required. So the maximum at the performance point, the actual base shear which we were getting is being recorded over here, and the design base shear which we had through the code, that is being shown over here. So if you compare both these values, they are divided as a ratio, and we have found out that the overstrength factor is 1.658. Then moving on to the ductility reduction factor, which we want to find out, that is ultimately again done through the maximum deformation and the yield deformation. This yielding deformation, again we are going to get it from the parameter which is discussed over here. So the performance point where we have, that gives us the yielding point. So we have the yield from the pushover curve, we are going to have the yield drift, the value, and this is the maximum limit available, which is available according to the code. Also we can say that is 0.004h, that we are giving to the structure also, and that is given in the code also. But how much achieving, how much we are achieving, that is being recorded as a yield point. Okay, so if you again see in this particular graph, that this is my place where I want to achieve the deformation, but actually I'm going at this particular point. So there is going to be a reduction in that particular point, and from there we are going to note it down. Okay, so we will find out the ductility value according to it, and based on our mu and phi value, the phi will be calculated using these values. The time period we have, the phi we can find out, and R mu will be calculated using this equation. So here instead of excuse me, instead of using Newmark and Hall, I have used the equation of Pareto. Now the estimation of the response reduction factor using all as a product of all, and we know that RR will be 1 because we have 4 vertical line in our seismic framing arrangement. If we had only 2 bays, the value would be changing, but as we had 4 beams or more than 4, we can directly take the value as 1. So we have found out the R value as 4.952 for a normal building without any infill wall. तो हमने infill wall नहीं consider किया है, और जो हमारा पहला मॉडल था, this one, what is the R value we have incorporated for that, and that is coming to be 492. In the similar manner, if we tabulate for all these things, the value of R is changing for each and every model. Here, if you see, the RS is changing, R mu is changing, RR obviously is going to be constant because it is based on the framing, and framing they are not changing. But these two parameters are changing. So let's have a pictorial view from the graphs. So if you see, the overstand factor is increasing obviously without having an infill wall. It is increasing, and when we consider on all the parameters, it is increasing almost 6 times, we can say, because one value is 1.66 and next is 7. So almost 5 times minimum, twice we can say. Even if we consider for a soft story and a ground story, the value is double, so minimum twice, we can say thrice over here, and 4 or 5 times we can conclude that the overstrength is going to increase. Same value for your ductility factor, if you consider, it is going to reduce drastically. Why it is reducing? The technical reason is because we have considered that as an strut, and that is going to help you to reduce the ductility, and that's why the ductility factor is reducing. How much it is reducing? Again, we have the values on the screen itself, and based on that, we have a variation of R as well for the model buildings. Now, if you focus, so obviously we have come to know that okay, the R value is not constant, it is changing, not only for one building, not for only for different building. Here we have taken only one building, I'm saying precisely only 5-story building, which has a constant height, constant zone, constant soil conditions, constant grades. Now you just imagine if everything is changing, what would be the values? So that is also a point to be concerned. Now, if I consider this value, the R value, which is an actual value which I'm getting and incorporating into my building, what happens or what are the consequences? Let's focus on that. Once again, I'm saying what I'm trying to say, that R value, instead of taking as 5, if I am modifying that value, which we are finding out using this equation and incorporating manually, अगर कोड ने जो हमें 5 वैल्यू दी है उसकी जगह हम ये वैल्यू इनकॉर्पोरेट करते हैं हमारे एनालिसिस में, तो क्या चेंज होगा वही हमें जानना है. सो दैट्स व्हाई वी आर गोइंग टू फोकस ऑन दैट पर्टिकुलर पैरामीटर. सो वन बाय वन विल सी दैट on the important parameters what it is influencing. So first, the value which Indian code is giving, that is tabulated over here. So the design base shear, forgetting about the value which we are getting through the software. Okay, we are using again the equivalent static analysis only, but instead of taking 5 value, I am taking a value which is found out using the theaters. Now as this value 4.95 is almostly near to 5, we won't find any change, almostly it is same. But as the values of R of other are being changing, so that factor is going to be changed and that is going to affect a lot. So here you can see that the design base shear for the Indian codes is is higher, much higher as compared to the one which is for the modified R value which we are calculating. So here you can see that is reducing a lot. For knowing, so the notations are again the same only, because writing the whole sentences was not convenient, so I have written the notations. This is for NIW, no infill walls, infill walls at the outer ones, infill wall at inner and outer, soft story at the ground, and soft story at the middle. Now, if I focus on the displacement part, the second important parameter which is important for an analyzer is the displacement. So if I consider the R value according to the given code, what is the thing that is displayed over here, and if I incorporate the actual value which we have found out using equation, so on the screen we can get the differences. That also is going to reduce in that particular the displacement is going to reduce only as the R value is almost 4.95 5 same. For this we are having the same, almost same values, rest everywhere it is effective. IDR, which we popularly known as interstory drift ratio, again that is also going to change, and that we are plotting over here and seeing the values in the graphical manner. So we can say the stiffness is going of the building is going to increase obviously using the infill walls, and when they are used, the ductility factor has been reduced a lot. The infill values is going to consider the overstrength factor as it is being there, and it is also going to consider the displacement which is there, and that also is going to be reduced. Here you can see the drift ratio is reducing for all the particular parameters. Some values which are found out in percentage comparing to the codal values. So how much increase in overstrength we have found out comparing to the building which is a normal one, which is having no infill wall. If I compare to that particular value, how much increase I'm finding in the respective uh, models that is being displayed over here. So if I considered uh, only, say for example, the least one, not considering the highest one, even the least one, I can see that it is twice the overstrength is increasing for, it is increasing 100%, so almost twice, four times, and so on. The ductility factor is also going to reduce in percentages, that is being found out over here. The R factor also is being increasing, that is being listed over here. Now this is not with the codal position, this is only considering, here the focus is being shown to us how an analyzer works or plays a role while analyzing, whether he should model that building as an strut or not, that is going to be focused over here. So if he takes it as an strut, how much variations he can get, that is being displayed over here. That minimum he can get 3% increase in the R value, or even if I focus for an overstrength, minimum he gets a 100% increase in that. Same values for the roof displacement, base shear, and interstory drift ratio is being displayed on the screen. So just have a view of the values, and so that will be more convenient, so we can have a glimpse. I won't read out all the tables, so you can just have a glimpse for that. Moving on further, the final summary, or the thing what I would like to say is implementing only. Now the summary is being focused right now primarily on the example which we have taken out. Okay, so that summary I would say is that the R value should be modeled, or it should be modified according to the given location. And if we see that the base shear was reducing to a drastic level, if the base shear is going to reduce, the elements are also going to be reduced, and we are going to save to a much economy. Okay, the ductility factor, if you see, for the models which we have taken as infill wall, whether it is outer, inner, soft story, or middle story, that was not having more variations. The more variation was there with a one which without infill and with an infill. So that was reducing drastically. If we see over here, the infill walls increase the overstrength factor up to a great extent, and reduces the ductility factor also. And there is an increase in R factor if you see for mostly all the models which we have considered over here. Okay, what I felt, or I would say, that when we model a given structure according to the actual value where you are designing that particular thing, it will ultimately prove to be an economical design. So every time if you model the R value and then we design accordingly, it will prove to be an economical design. So it will be ultimately helping to the economical development and ultimately development of the country. So that is a very important parameter, so it should be implemented in the code itself. And the level of damage which is there, it is uh, not only should be based on the seismic zone or the fundamental time period, many other parameters are also there that should be incorporated. The soil type is also very important parameter where it should be governing. One important parameter is again a durability concern, okay, which we had a first lecture, and Rahul sir had delivered that. And based on that also, when durability comes into picture, how much lifespan we require for a particular building, that should also be governed. And based on that also we can reduce or increase the R value. That provision should be given to us, means the designer. So the Indian codal provision should provide R value based on the corresponding ductility value and overstrength value. And because other countries are also doing that, so we should also do that. Okay. uh, these are the references from which I have worked on. And thank you for the presentation. Firstly, the questions obviously I'm going to take, but please be feel free to contact me anytime if you require any help regarding the analysis portion. The details are given over here. And uh, a very few points I have covered in this. So as an analyzer, if you see, there is much more significance which is to be given while analyzing any structure. That what is the main concern, how it should be done. If you can't visualize it, you can't do it. Okay, a very brief example if I give, that for bridges we are giving roller supports. So that roller support which is being given, that is for a specific reason, that if we don't give a roller support, if we, as we have seen in the example, that giving fixed support is beneficial in changing in helping for the deflection and bending moment. But there we are going to have your lateral movement. If the lateral movement is going to be restricted, there is going to be lateral displacement which is there in the beams itself, the bridge deck itself, and that is going to cause harm to the structure. So for that, rollers are provided. So again, a significance of an engineer is there as an analyzer. So for each and every case, I would say for each and every case, we should analyze it according to the requirement. There should not be any prescribed format that, okay, if this is the case, this should be the answer. If this is the case, this should be the answer. You should try to understand the concept. You should try to understand the importance of the structure, the purpose of the structure, why it is provided, and then apply the conditions which are more suitable to us. Okay, even if I say that now we have softwares which are the best tools, usually designers don't do that. They just run the analysis. When it's safe, they give it up. Why can't we go for an ergonomics design? Why can't we go for an compatible design? That is it more convenient to go for an concrete structure? Is it more convenient to go for an steel structure? Is it more convenient to go for an composite structure? Or if I provide a grade of M20 and FE415, or if I provide a grade of M25 and FE500, what are the consequences for it? We don't have to construct the whole building or the whole structure. We just have to analyze the structure. So through that analysis, what impact it is governing, what changes it is bringing to the shape of the element. The shape of the element again is one of the vital parameter which we usually have to understand. A very basic or simple example we know of a ruler scale. Okay, usually we used to play in our childhood days, even I used to play right now also. What we do, we bend the scale like this, and sometimes it fails, but we cannot bend it when it is in vertical manner like this. We cannot bend it like this. Why? because the moment of inertia is increasing, same section is being just rotated. Now as an engineer, you should come to know how your orientation should be play a role, because the concrete is going to be the same, the structure is going to be the same, whether you are going to use a steel section, the C section, whether you're going to provide like this or you're going to provide like this, the weight of the section, the cost of the section, the labor of the section would be same. But what is the importance of as an analyzer is the orientation, is the importance of it, how we should understand the placement of it, which type of support we should go. So in these ways, I would say the topic which is being discussed over here for the R factor is at a very higher level, and even for nominal level, we should consider each and every parameter very, very, very carefully. It is it is not that we can bluff anything that okay, take it as fixed support and analyze the building. There will be consequences. Changing only to a fixed support will add fixed moments. It will add negative moments. So is your structure capable of taking that fixed support? Is actual the situation available in field that you can go for fixed supports? So that is also a concern. So there are n ways in which an engineer can play a very vital role for changing the parametric study and changing the whole concept of the project. If an engineer wishes, he can reduce the cost to half also, but that requires that skills, and that skills comes through analysis. So analysis is one most important parameter, and it plays a very, very, very significant role in the life of an engineer. So this was the topic for the day. Thank you very much for the patience listening, and you're again anytime welcome for any questions. You can note my email ID or my contact number, and if I would be happy to help you out for questions right now also. Please.
Thank you so much, Nirav sir, for your enlightening lecture. And it was very easy now, I guess, for everyone to understand how we could start analyzing the structure with a very few steps only. That was very wonderful, sir. You have explained it very well. Thank you so much, sir. Now the forum is open for the question answer. Participants, anyone wants to ask anything, you can ask Nirav, sir. Anyone wants to ask anything?
No, ma'am.
Okay, then. Well, done for the day today. Once again, thank you so much, all the participants and Nirav sir. Just like yesterday, after this session, we are going to send you the feedback link on the WhatsApp group. Please mark the feedback. That would be a feedback come attendance sheet for us. And we'll see you tomorrow on the same time. Okay, for the same lecture. Okay. Have a nice day, guys.
Thank you. Same to you, ma'am.